So in the previous video about just the general idea of Bronsted-Lowry acids and bases, we briefly discussed how water can be amphoteric. It can act as both an acid and a base, right? Because of that, we know that we have to have some ions present. There has to be some OH present, there has to be some just general protons present, and those turn into H3O plus. But what we end up having is a process called autoionization. So if water is acting as both an acid and a base, then you will end up having these ions in solution, and then from there you will have water react with itself. That's where the autoionization comes into play. So because of this, you will have both H3O and OH minus in solution. So you have like one water molecule. Let's say if you want to look at it like they're reacting with each other, you have one water molecule taking away one from the other one. That's where you get the H3O plus. And then what's left from that one that got the proton taken away is just the OH minus. So we have these ions in solution in aqueous solutions. The concentration of H3O plus and OH minus in water are exactly equal. So we know that in water, the concentration, right? Anytime you see brackets, it's just concentration. So the concentration of H3O plus, hydronium, or hydroxide, OH minus, is actually 10 to the negative 7th molar. So it has a very specific concentration, 10 to the negative 7th, specifically at 25 degrees C. This is just like common room temp. That's the concentration of either of them in water at 25 degrees C. So keep this number in mind. We can calculate something called the ion product of water. This is whenever we multiply the concentration of hydronium and hydroxide, and we get our Kw, the ion product of water. Because we know that the concentration of each of these is 10 to the negative 7th, right, or 1 times 10 to the negative 7th, when we multiply these together, we end up getting 1 times 10 to the negative 14th. And if we measure a concentration of one or the other, we can calculate whatever unknown you have. So because we know that overall Kw is always equal to this, the concentration of both of our ions, hydronium and hydroxide, is equal to this at 25 degrees C in water. If we measure one of them, we can find the other. And this relationship between hydronium versus hydroxide is actually inversely proportional. So if hydronium increases, then OH has to decrease. So that overall, the product, which is 1 times 10 to the negative 14th, stays constant. So here we have our first example where we are examining the inverse relationship between hydronium and hydroxide. So a solution of acid in water has a hydronium ion concentration of 2 times 10 to the negative 6 molar concentration. What is the concentration of hydroxide ion at 25 degrees C? So first, we need to think about what this is asking about. This is asking about the inverse relationship, which has to do with our Kw, the ion product of water. Kw is equal to the concentration of hydronium times the concentration of hydroxide. And we know that overall, this always equals 1.0 times 10 to the negative 14th. But also, we can't forget that this is a reaction that's happening, right? For our ion product constant, we actually have two water molecules, remember autoionizing, to form hydronium, which is aqueous, and also hydroxide, aqueous. Water is obviously a liquid. So because of this, we know that the only factors that affect our Kw is obviously our ion. So that's why the water molecules, remember liquids and solids aren't included in equilibrium constant, so it's the same thing here. The Kw does not include the water molecules. That's why it's only the ions. I just wanted to point that out because I realized I didn't earlier on when I was talking about Kw. But anyway, this problem is asking about an acid in water, and we know that the hydronium concentration is 2 times 10 to the negative 6. So we know that H3O is equal to 2 times 10 to the negative 6 molar. We know that overall Kw equals 1 times 10 to the negative 14th. Our unknown is our OH, right? Our concentration of hydroxide, or OH minus. So we are going to solve this for our OH minus. And it's easy, we just divide both sides by H3O, the concentration of our hydronium. That cancels that out, and then I'm just going to rewrite it, make it neater. So I'm flipping it around, and then we have our Kw divided by H3O plus. And both of these values we already have. We have H3O right here. We have that checked off. And we also know that Kw equals to that. So we have both of these, and we just plug them in. So now I'm going to write them in. 14th. And then what you should get from this is 5.0 times 10 to the negative 9th. So that is our concentration of our hydroxide ion. And you can go back actually and double check and plug this in to here along with your hydronium, and you would end up getting the 1 times 10 to the negative 14th. So an amphoteric substance is one that can act as an acid and a base, such as water, right? The requirements for a Bronsted-Lowry acid or base is that you have lone pairs available to accept a proton for a base. And for an acid, definition of Bronsted-Lowry is that you have to be able to donate your proton. So as long as you have some sort of lone pair and also a proton somewhere in the compound, in the molecule, then you can act as both. And an example of this is our HSO3 minus polyatomic ion. This polyatomic ion can act as an acid with OH, and it can act as a base with HI. I'm gonna leave that in there. So we're just gonna write these out. So I mean, the problem tells you what it's reacting with, so we're just gonna write these out step by step. So first we have HSO3. Obviously this is aqueous because this is acid base. All of these reactions are in water. And then it's reacting with OH. OH is an ion that's aqueous. And what's going to happen now is that the proton is going to be donated from our HSO3 minus, right? If it's acting as an acid, then that means this proton right here that I'm underlining will go with our OH minus to form H2O. I know it's written differently, right? But if you wanted to, you could write out HOH and you would see, okay, that's H2O. So you get H2O, and H2O is a liquid, it's not aqueous. It's the actual molecule itself. And what we're left with is SO3, 2 minus, aqueous. So this is our HSO3 minus written as acting as an acid with OH, hydroxide. And next we're going to write it as acting as a base with hydroiodic acid. So here we have HSO3 minus aqueous, and it's reacting with our hydroiodic acid. So now what's going to happen? Instead of it giving up that proton the way it did in part A, it's going to accept a proton from the hydroiodic acid. And it does this because there are lone pairs available to take that proton. So what you end up getting is H2SO3, and that takes away that charge. Remember, protons are positive. So if you have something with a charge and you add a proton to it, it's going to make it neutral. This is aqueous. And then we end up having that iodide ion on its own. Everything's aqueous. So here we wrote both the two different types of representations of this amphoteric substance and how it can act. So we talked about how water, pure water, will have the exact same amount of both hydronium and also OH minus, right? It has exactly 1 times 10 to the negative 7th of hydronium, and also the same exact value for the concentration of hydroxide. That is pure water, or also neutral solutions, but it's easier to think about pure water first. Acidic solutions will have a larger hydronium concentration than OH. And anytime you see hydronium, you should think of just regular protons, right? So if you have a lot of protons, they're going to combine with our H2O, and then you get the hydronium. So that's where that's coming from, just reminding you. But acidic solutions, because you have so many protons in solution, you end up having a lot of hydronium, greater than the amount that is present in neutral solutions or in pure water. And OH will have less than that 1 times 10 to the negative 7th. Basic solutions are the opposite, so they'll have a higher hydroxide concentration in comparison to our hydronium concentration. So main idea here is acidic solutions have a lot of hydronium, basic solutions have a lot of hydroxide. You have probably heard of this term, either in outside like TV or life, or any situation that isn't actually like science class. You have probably heard this term, but we're going to break it down and actually talk about what this value means and how it relates to what we can say about acid strength. So the acidity or basicity of a solution is often expressed as pH. pH mathematically is this calculation right here. The negative log and then the concentration of your hydronium or protons, whichever one. It could also be negative log, just H plus. Same thing. So what pH does, and the reason it's useful, is it takes a very small number and it makes it into a number that we are able to work with a lot easier. And that's true for any log calculation that you do. It takes either a really big number or a very small number, and it makes it something easier to work with. I don't know if your math teacher ever explained it to you that way, but when I finally realized that that's what logs were, it made my life so much easier. So all log calculations, all they do is make a either really big number or very small number something easier to work with. So let me show you what I mean. So let's say we have H3O plus, right? And the concentration is 1 times 10 to the negative 5th. Okay? How do we make this very small number? Because that's what it is. If you converted it to regular notation, it would be like 0.0000, like that. So it's a tiny number. And honestly, we don't really understand how tiny that is, right? Like our human brain can't really visualize or be able to connect how small that is. So what we do is we take the log of it. What does log do? Log takes that times 10 to the, and it makes it into whatever exponent it is. So this is why this says this right here. pH is the exponent on the 10. So here we have a 10, but with a positive sign. So you see how the exponent here is a -5? What pH does is it makes it into this value, 5. So instead of having, oh, the concentration of H3O plus of hydronium is 1 times 10 to the -5th, you can just say the pH of this solution is 5. You see how much easier that is? Isn't that a lot easier? So that's what the negative log does. It takes the exponent down, makes it into a number, and it puts a positive sign in front of it. So if you were looking at the pH of water, you would take the concentration of hydronium, which is 10 to the -7th right there, take the negative log of it, and you get 7. Isn't that so much easier to work with? So you need to know the concentration of hydronium in order to find the pH. If you have a pH less than 7, you consider the solution acidic. So this particular solution that I just, just talking about a general solution, would be acidic because the pH is 5, so it's less than 7. If you have greater than 7, it's basic. If it's equal to 7, it's neutral. So this is the overall relationship here, that the pH is that exponent. Here we have some just general pHs of very common substances. So the juice in your, which is gross that they call it like that, gastric juice, gross. The acid in your stomach, the pH is 1 to 3. That is extremely low. The pH of sodas, between 2 and 4, very acidic. It's all that phosphoric acid. The pH of peaches, around 3 something, and a bunch of other ones. And then look at these really basic ones: milk of magnesia, household ammonia, and then like pure sodium hydroxide, almost high, very, very high, 14. Okay, so we talked about how pH relates to log, right? The log of whatever hydronium concentration that we're looking at. Now, what if you have a number in front of that times 10 to the, right? So with log, we were saying, okay, you're going to take the exponent, bring it down, you make it a positive value. But what happens if you have another number over here? Because for that particular example, I just had 1 times 10 to the -5, -7. So the 1 really didn't affect anything. But here we have 2 times 10 to the 6. How does this affect the overall value you get from this calculation? So the log of 10 to the 6 gives you 6. The log of the 2 gives you 0.30303. When you combine these two, you get 6.3. So that's what happens. The decimal part that you get from calculating a pH will come from this part of this number in scientific notation. It comes from the digit in front of the magnitudes of 10, okay? So this contributed to this whatever underline, and then this right here is what contributes to that number before the decimal. So because we know that sig figs come from this value right here, right? It never comes from our magnitudes of 10. the sig figs in a pH value will only be the digits after the decimal point. So here we started off with 2 sig figs. For the final pH, we only want 2 sig figs after the decimal point. This first value at the beginning is not affected. You just leave it there how it is. Finally, just to connect again the pH to the hydronium concentration. So here it says proton concentration, but it's the same thing, hydronium concentration. It's interchangeable. So we know that the pH basically brings down whatever value you have on the exponent, and it makes it into an easy number to look at. So the lower the pH, the more acidic the solution. So here you can see that as you increase, this is increasing amount of hydronium. It's increasing because your negative exponent is getting smaller. If your negative exponent is getting smaller, that means your number is getting bigger. So overall, this is a bigger, larger amount of hydronium. So because you have more, we know that there's more hydronium over here, the corresponding pH values are more acidic. So if you have a pH of 1, that's very, very acidic. Whereas the opposite is also true. So if you have a very small number, so for example, 10 to the negative 14th, it's a very tiny number. Like if you wrote that out in regular notation, you would be like, oh, that's a bunch of zeros in front of that 1. A very small number. So whenever you take the pH calculation of it, it's a very large number, 14. So the overall range is 0 to 14 that we work with. So whenever you have a pH of 0, your hydronium concentration is 1 molar. Whenever you have a pH of 14, your hydroxide concentration is 1 molar. We can also express acidity or basicity in terms of pH. This is less common. Most commonly, you'll just see pH, but it is possible, and it's basically like the complete opposite. So instead of taking pH, you take pOH, and it's the negative log of our OH, our hydroxide concentration. It's the same exact idea, but with hydroxide concentrations. When pOH is less than 7, we have a very basic solution, because less than 7 means you have a higher concentration of hydroxide. And when pOH is greater than 7, you have an acidic solution. If you want to add up the pH and the pOH of a solution, it should add up to 14. So if you calculate that the pH of a solution is 6 and you calculate the pOH of it, it's going to be 8. They're going to add up to 14. And then this chart, I really like it because it shows you the pH versus the pOH, and then it shows you the concentrations, and it also gives you some examples. So coffee is actually pretty acidic, which isn't good, and explains a lot of my heartburn sometimes. But you can see the H3O concentration, the pH of it, right? Remember, corresponds to that exponent, the power of it. I didn't mention this, but P is about power, the power of the exponent. So for hydroxide, it's a lot less, it's a lot smaller. So the pOH is 9, corresponding to a high acidity, right? High acid. And I would say just take a look at this table, try to connect the dots between everything, and kind of talk yourself through it so that you understand all of these things. Like I said, pH and pOH add up to 14. So because of that, if we have a pOH, we can find the pH. Or if we have a pH, we can find the pOH from that value. So this first example is asking us, what is the pH of stomach acid, which is a solution of HCl, with a hydronium ion concentration of 1.2 times 10 to the negative third. all we have to do is plug it into our equation. So it'll be pH equals negative log of our concentration. pH has no unit. I just wrote in molar, but overall it's not going to have a unit. When we take the negative log of this, or first when you take the log of it, you end up getting negative 2.92. And then when you multiply that out, you end up getting a positive, so 2.92. Now think about it. Does this make sense? Our power was 3. And overall, this pH is around 3. So this does make sense for you to get this pH value. And remember that the amount of digits you keep here on the end of your pH is related to the amount of digits you started off with on your scientific notation value of your concentration. So right here is 2 sig figs, so you should end up with 2 sig figs right here on the decimal portion of your pH. So our pH is equal to 2.92. So in terms of how you plug this into your calculator, you would just put a negative, the negative sign, and then the log, and then enter your concentration, close parenthesis, enter. Here we are calculating the hydronium ion concentration from pH. So this is a little bit different. We are going to do something a little bit new that we haven't really discussed just yet, but it's okay, it's not hard. So because we know that the relationship between pH and hydronium concentration is pH is equal to negative log of hydronium, we can also work backwards. So if we are given the pH, so in this case 7.3, right, calculate the hydronium ion concentration of blood. How are we going to do that? We already have the pH. How are we going to go backwards to find this hydronium concentration? What you're going to do is solve for it. So we know that overall we have negative log hydronium equals 7.3. First and easiest thing we can do is multiply both sides by -1. That cancels out that negative right there. Now we have a negative. So now we have log H3O equals negative 7.3. You're at a good spot. Now what we need to do is take away that log. How do we take away a log? You raise it to 10. So we are going to raise this entire number to be the power of 10. And then you're going to do the same thing here. 10 to the raised to the negative 7.3. What we're doing right here is called the antilog. Again, just some math, but it's called the antilog. And you literally just type it into your calculator exactly like that. Now what this antilog does is it cancels out that log right there in front of the hydronium, and all you're left with is hydronium concentration equals 10 to the negative 7.3. And like I said, you just type it in exactly in that way. So you type in a 10, you raise it, press the little button that lets you raise, and then type in negative 7.3. And then press enter. And then from this, you should get 5 times 10 to the negative 8th molar. So how did I decide how many numbers right there to keep? So that is based off of the value, the decimal value that you had on your pH. So here I only had 1 sig fig, so I'm only going to keep 1 sig fig here on this digit. And that would be the process of going from pH to hydronium ion concentration. So basically like the opposite. So the new thing that you learned here was about antilogs. And finally, we have another example. Here we have a concentration of our potassium hydroxide. So what this is telling me is that I have the concentration of hydroxide. How do I know this? Because potassium hydroxide is a strong base. Strong bases completely dissociate. So whatever the concentration of potassium hydroxide is, that automatically tells me the concentration of hydroxide. So 0.0125 molar. Now we know that we can calculate pOH from negative log concentration of hydroxide. So we can go ahead and just plug that in, negative log, and hopefully I think you can see where I'm going with this. But once you plug that in into your calculator, that's easy, you should end up getting 1.903. So we have the pOH, and remember that the pH plus the pOH equals 14. So because of this, we can solve for pH. We found pOH already. We need to solve for pOH. So I'm going to subtract pOH from both sides. You're probably like, duh. And then we get pH equals 14 minus the pOH. And in this case, it's 1.903. And then I end up getting 12.10. So we found the pH and we found the pOH, right? Very simple problem. So as long as you kind of know these definitions, right? Knowing that, and also knowing this right here, the fact that it's equal to 14, those are the important points from this.